All right, in this chapter we're going to talk about subspaces and spanning sets. Now really what we're going to do is go back over and revisit some of the concepts we've already been using and put it on a more firm theoretical basis. Now, this may seem like an unusual approach in a textbook, but in fact mathematics often does this. The calculus that you use was developed after hundreds of years of people using calculus in a very seat-of-the-pants way. So, until now you've been talking about vector spaces, linear combinations, subspaces, in a kind of seat-of-the-pants way, and now we'll put some firm theoretical underpinning to those concepts. All right, so here are some questions that we'll address. The subspace, when is a subset of a vector space itself a vector space? Right, so you can have a vector space inside a vector space. Just to spill the beans a little bit, this picture shows a plane inside a space. Now, plane is a vector space if that plane contains the origin. So this is a subspace inside a subspace, inside a vector space. A vector space inside a vector space, which is called a subspace. So how do you tell when a set of vectors is a subspace? That's a good question, and we'll address that question. Linear independence. Given a collection of vectors, is there a way to tell whether they're independent or if one is a linear combination of the others? Now, we've actually solved problems like this, but again, we'll put this on front and center and make this an explicit question and give a very clear answer. A dimension. Is there a consistent definition of how big a vector space is? Now, we've been talking about 2 dimensions, 3 dimensions, plain 2-dimensional, space is 3-dimensional. But let's put that on, again, on a firm theoretical basis. And finally, basis. All right, how do we label vectors? Can we write any vector as a sum of some basic set of vectors? How do we change our point of view from vectors labeled one way to vectors labeled in another way? So basis is basically a framework that is used to define all the vectors in a vector space. Now, canonical example of basis are the x, y, and z vectors in 3-dimensional space, the 3 coordinate vectors. So that's called the coordinate basis or the elementary basis or the fundamental basis. But basis in general is a set of vectors that can be used to express any vector in a vector space. And a vector space may have more than one basis. All right, you may not have absorbed all of that, but we'll come back to those concepts and let's go on. All right. So, definition, a subset U of a vector space V is a subspace of V if U itself is a vector space under the same addition and scalar multiplication operations of V. And you should keep this picture in mind. Big space, 3 dimensions. Right? You can go in basically 3 directions. This direction is perpendicular to this plane. This plane also, if you add any 2 vectors in this plane, you'll remain in the plane. If you walk along the plane in any direction, you can't get off the plane unless you jump. But if you move in directions along the plane, you always stay within the plane. So the plane itself can be considered as a linear space or vector space. One way to define a plane is this way. And we've talked about that. This is the definition of hyperplane. You take x, y, and z are your variables. A, b, and c are constants. Form the vector ABC. And this is simply expressing that the vector x, y, z is perpendicular to the vector ABC. All right, so that's what he says down here. So the set of vectors that are perpendicular to a fixed vector is a plane through the origin. Now, it turns out that any 2 vectors that are both perpendicular to ABC, if you take any combination of those 2 vectors, it's still perpendicular. And you can do that and prove that. It follows by the linearity of this matrix product. Right, if I write x, y, z, so let's do it a little more explicitly. All right, so we can say suppose ABC times, and we'll just say x1, y1, z1 is equal to 0. Now you can recognize this also as the dot product. And let's suppose also that ABC times x2, y2, z2 is also equal to 0. All right. Then we have ABC times this vector here, x1 plus x2, y1 plus y2, z1 plus z2. So if I add these two vectors, x1, y1, z1 plus x2, y2, z2, I get this vector here. And you just simply rearrange that. That's going to be a times x1 plus x2 plus b times y1 plus y2 plus c times z1 plus z2. And of course you can distribute and reassociate, and that's the same as a times, it's going to be the same as ax1 plus bx plus by1 plus cz1. See, what I've done is I distributed the a and taken out the first term within each one of these additive terms. And then I also have left over from that plus ax2 plus by2 plus cz2. And the result is equal to 0. All right. Okay. So what does this show? This shows that the sum of any two perpendicular vectors is still perpendicular. Right? You could similarly say that if I take ABC and I take that multiplied by some constant times a vector, kx1, y1, kz1, then I'll get I'll get a k1, akx1 plus b ky1 plus c kz1, and I can factor out the k. That's equal to k times ax1 plus by1 plus cz1, and this thing is 0. That's just 0. Right? So the whole thing is equal to 0. So if I multiply a vector by a constant, and that vector is perpendicular to ABC, then the multiplied vector is still perpendicular to ABC. Now geometrically this is very clear, but now we see it algebraically as well. So the geometry and the algebra agree together. So that's what he's expressing here, that in fact we can both multiply and add vectors arbitrarily and still get vectors that are perpendicular to a given fixed vector. Now he's calling this ABC a matrix. Just think about a vector as a 1 by n matrix. But you can, with equal validity, call this a vector or a matrix. All right. Now, so we see this property that any combination, any linear combination of two vectors in the subspace are still in the subspace. And in fact, that's the defining property for a subspace. And that's what is stated here in the subspace theorem. Let U be a non-empty subset of vector space V. Then U is a subspace if and only if mu U1 plus nu mu2 is in U for arbitrary U1 and U2 in U, and arbitrary constants mu and nu. In other words, take any two vectors in your subspace, form any linear combination of those, and it must still be in the subspace. And again, if you go back to the plane and see that example, take this x1 and x2, any arbitrary linear combination of x1 and x2 must be in the plane. So keep that picture in your mind, and it will help you to understand. And now, the proof is pretty straightforward. Now, since this says if and only if, you have to prove things two ways. You have to prove that if U is a subspace, then linear combinations of vectors remain in U. And you have to prove that if linear combinations of any two vectors remain in U, then U is a subspace. Now, as he says, one direction is easy. If U is a subspace, then it must be true that any linear combination of vectors in U is in U, because that's the closure property, which is one of the properties of vector space. On the other hand, what you have to do, if you have this closure property, and the fact that U is a subset of a vector space, you can get all 10 properties of vector spaces, because most properties in a vector space are inherited. That is to say, if it's true for a larger set, it's true for a smaller set. For instance, the distributive property. If we have the distributive property true for a large set of vectors, it's also going to be true for any smaller set of vectors, because they're just part of the crowd. All right? So we have that proof in both ways. Now here it says that the condition is that if any linear combination of vectors in U is in U, then U is a vector space. Now you can treat that, you can check that in two steps. You can say if you add any two vectors in U, do you still get a vector in U? And if you multiply any vector in U by a constant, do you end up with a vector in U? So sometimes it's better to check the two separately, and sometimes it's better simply to check whether a linear combination of vectors in U is in U. In other words, sometimes it's better to just check this directly. Either way is fine, whatever you're most comfortable with.